Uh, okay. This is advice on building the circuit, and there's one pertinent piece that I just came up with recently, just now, thinking about it, and then some other pieces of advice I already know about, but I don't know if I've stated it in prior videos, and so it's worth repeating from my standpoint for the sake of your benefit, in case you want to build this circuit. The piece of advice I just came up with this morning has to do with frequency. When I run the simulation, I run it such as I do for my own convenience. It doesn't mean that it should be done that way. So when I run it like 20,000 cycles per second, the input, the frequency, the sine wave generator, when I run it at 20,000 cycles per second, that's for my benefit, because I need the results to occur, the computer to compute, the software, the microcap software to compute the values and spit out the data within a reasonable amount of time, consuming a reasonable amount of space on my hard drive. That's why I choose either 20,000, 50, or 70,000 cycles per second tops. Now, I have gone as high as 1.35 megahertz, but the simulator won't allow me to go any higher. And if I go any lower than 20,000 or 16, I believe I used 16 point something thousand cycles per second, I have problems. Usually, well, sometimes the circuit will collapse and go comatose, but that means for the most part die. But sometimes it doesn't. It just takes longer to compute the results. Now, there's another problem. See, what happens when you use a lower frequency, the spacing between the staccato wedge peaks and troughs, because we're developing a surge, and the surge happens because of a capacitance occurring between the transfer coil and the voltage coils, for the most part, and that capacitance, that inductive capacitance, is what creates the surge. And then we use the spark gap to cut off the surge periodically, and that creates the staccato wedge-shaped surges. And the frequency of those staccato wedge surges is what I'm referring to, is the main problem I came up with this morning that has to be dealt with. And that is that if you have the spacing between the staccato wedges too far apart, you're going to have several problems. A, you're going to have a lot of warm-up time before the first staccato wedge even occurs. And this could be several seconds that you're sitting there waiting. It could be minutes, it could be hours. I've done, actually, as I recall now, I've done simulations in which in real time, not the time the simulator runs on the computer, but what the simulator is telling me would happen in the real world if it, what it's simulating. Something like 14 or 16 hours to wait for the very first staccato wedge to occur. I mean, that's quite amazing. Or it can be something like nanoseconds. Yeah, I think I've done this, where the warm-up time is literally a matter of nanoseconds, literally, not figuratively, nanoseconds. Now, when the warm-up time increases or decreases, you also get a comparable shift in the spacing between the staccato wedges once you put in the spark gap to create these pulses, these surging pulses. So when the warm-up time decreases, the duration between the staccato wedges also decreases, and likewise, when one increases, the other increases. Now, besides the warm-up time being an issue, we have the issue of the spacing between the staccato wedges themselves. And that is, when I do a simulation, I try to always look at the RMS value, because that's what comparable power I'm looking at, that I want to evaluate. Well, what is my circuit creating? What is what is it putting out? My target, I have a target for a certain output level. But I forgot to mention, and it's worth mentioning now, that there's a trade-off. That if you do, and there are various factors that regulate the warm-up time and the spacing between the staccato wedges, and the frequency input of the sine wave generator is only one of them. You have basically all your components are going to impact either the output level or the frequency of the staccato wedges, and usually both, actually. And usually it's a trade-off. You'll get more power, and then the wedges will space themselves out more, and you'll get a longer warm-up time versus bringing in the wedges and compacting them and shortening the warm-up time and shortening the duration between the wedges, but at the cost of your output power. It's not a lot of cost, one versus the other, but you do cost. There is a juggling act there. I'm already losing my voice. But the issue is, if you allow the space between the staccato wedges to occur too much. Now I said it was at a cost, right? What that means, but see, the cost is not a big deal, because think of it. What we want is the RMS. That's the target. What we don't want is for the staccato wedges to become too severe to make up the difference, because then what happens is we're not going to have the kind of output that we want. Instead, we're going to have these huge surges. And they might happen, let's say, take an example, once every second. And I'm talking voltage surges, huge voltage. There'll be a current surge too. There always is, but for the most part, we have to deal with voltage. And that means a problem of arcing, the insulation drying out and cracking and arcing. Now, there are remedies for that I should try to remember to get to, but still, you don't want that. You want to reduce your hazards, right? Because you're dealing with an electronic explosive device by nature. It's like the, what was that? I forget the name of it. It starts with a CH. The Challenger. The Challenger mission that blew up and took the people with it. When they sit on top of that huge rocket at Kennedy, Space Center, whatever it is, in Texas or Florida, I forget where they launch. They're sitting on top of a bomb, and most of the time nothing happens. But once in a while, disaster happens and the thing blows up. And that's the risk we take when we build this thing. Is a statistical risk that you can expect it to blow up. You have to. You can't avoid it. It's the only reason why. Well, one of the main reasons why I don't build anything is because it's safer that way. I just simulate it, and nothing physically blows up. But I've blown up a lot of simulations. More than have gone comatose, because I know how to create the surge. It's like a skill or something. It's innate, and I just home in on it because that's what I want, because that's where I know where all the power gain is. And in all likelihood, it's capacitive reactance that I'm homing in on, because that's where the power is, but that's also where the danger is too. Inductive reactance, yeah, you can get a little over unity, but it's a trickle. It's like, 10% or something, It's nothing to get too emotional about. And Peter Lindemann, he had a device that is criticized on the internet, a whole article that I took issue with, because they were criticizing it, because Peter Lindemann gave up on it because the gain was not worth sneezing at. He wasn't even sure about his results when he got done with it, because the gain was so small. But if we look at the Edwin Gray motor, that thing put out nearly 300 coefficient of performance better than its output better than its input. That thing was an explosive device, and that probably was using capacitive inductance. Excuse me, did I say that right? Reactance, capacitive reactance, to achieve that kind of output. And all because of Richard Hackenberger. You know, Marvin Cole made it levitate, but Richard Hackenberger converted that levitation ability of that device into a formidable output device. And it was explosive. They were blowing up batteries before they knew what to do with all that excess energy. Anyway, be that as it may. Our job is to not allow it to explode in the first place, but it's precarious because you got a window. You have all your parameters, which means all of your components and their values and their arrangement. And then you have the tweaking, the tuning. And the resonance or the sweet area for tuning the circuit come in multiple, they may be infinite, but within your complex of parameters, if we glob them all onto one linear arrangement of conceptualization for the point of discussion, they come in infinite sets. We don't know how many there are. And there are gaps between the two in which either you go beyond the limit of one window of sweet area and the thing explodes, or you go less than and the thing goes comatose. And in between the comatose state of one sweet area, in between the explosive, the upper boundary of one sweet area, and the comatose or lower boundary of the next one up the linear line of this conceptualization, nothing. It just sits there comatose. But meanwhile, when you left the lower boundary, you had to explode to leave it, as you took it too high. Or if you left it in the opposite direction and went down the spectrum of sweet spots, the thing goes comatose and dies on you very quietly. So now, microcap, I did an experiment one time in which I did a circuit, not this, but I did a different type of circuit. And I did the exact same circuit in LT Spice versus microcap. And I got slightly different results. And that proved to me an important lesson. It proved to me that, see, I do everything in bite-sized pieces because that's the only way for me to attack this problem. Because we're learning something that can't be taught because nobody teaches it. They don't want to. It's dangerous. And it takes a dexterity and a certain amount of risk to be able to create free energy to this degree without killing and hurting anybody. Maybe killing, but at least hurting anybody. Because one guy almost took off his arm, he said, when his device exploded. And another fellow had shrapnel going in all directions, and he had to run out of the place to save himself. Anyway. Let's see, where was I? Oh, there's noise in the background. It's very distracting. I lost my train of thought. Oh well. So, the risk is in having the staccato wedges too far apart. And so your output level will go up, but it won't do you any good because your RMS will go down. And we don't want that. We want to keep our RMS high, and we want to keep the peaks of the staccato and the troughs of the staccato wedge narrowed into the midline, the oscilloscope, the zero, the midline. We want to keep them narrowed down so that we get less extremes, because otherwise we're going to be subjecting the circuit to a lot of stress, voltage stress mostly, but also current stress. And that voltage stress is going to wear out components, wear out resistance, and cause cracking and eventually arcing, and then the thing blows up. It might be fine for a week or a month, and then it explodes, and we don't know why, because we stressed it. There's a certain, especially in the early stages of development of something, a new technology, there's a certain amount of maintenance. When they put an aircraft on the ground, they have a routine of maintenance, of safety, that every so many hours of flight, they have to let the mechanics take a look and overhaul everything, and steam clean everything, and grease everything, and replace anything that looks worn, because they have to check. They can't just assume everything is fine. I'm imagining that that's the way it is with this circuit. It takes a certain amount of maintenance. So although it's free energy, there's added work of service. You're going to have to service the circuit, take it apart, look at it, inspect it, make sure everything is fine and dandy, and not just ignore it and assume that everything is fine because it's running now fine. Tomorrow it may not. It may explode in your face or go comatose, and you don't know which way it's going to go, because it's a very ginger balance to maintain this thing within the boundaries of one particular sweet spot that you have tuned it to operate within. And the lesson I learned from LT Spice and Microcap, to finish that example, that little tangent, is that reality is its own simulator. Microcap is another, LT Spice is a third. And I compare all three, and I leave out Paul Falstad because Paul Falstad's simulator is not realistic. Don't listen to anybody who says otherwise. It's not. It's a good learning tool, but it's not realistic. And it was a great way for me to learn, but it's not a great way to design anything to build. If you want to build something, you got to build using Berkeley Spice, and Berkeley Spice is what Microcap is based on, and also LT Spice, but they're two different flavors of Berkeley Spice, and so they give slightly different results. And so I'm imagining that reality is a third variety of Berkeley Spice, because, well, I can only estimate that that's what's going to happen. That I may fine-tune it in Microcap, and I prefer to stay in Microcap. I don't like LT Spice for various reasons. So I stay away from it, even though it's free, but you get what you pay for when it comes to simulators. So I stay in Microcap. So I imagined that reality simulation, namely building it, is going to be slightly different. And so whatever works, whatever you see I do in Microcap may not work when you build it. It may just sit there and you'll think, shit, you know. Like some people have on Facebook, one person has actually said, well, I did what he suggested and it didn't work, so I guess free energy doesn't work. No, you're just not willing to do the work to fine-tune it. If it actually is true that it can work at all. It takes work. You know, free energy is free, but you make up the difference with servicing the circuit and working to develop it initially, to get it to work, to fine-tune it. So many times I've heard people say, well, it worked in the shop, in the lab, and then when I wanted to go to the conference and display the circuit, I couldn't get it to work. I had problems tuning it, and we didn't get to demonstrate how well it works. Oops, you know. You know, it means maybe the circuit wasn't developed enough so that those kinds of hazards would not occur at the last minute. It's possible. That's why I'm not so sure I can scale it down too readily to work for a table model like an appliance. I got it to do that, but I didn't have the Oliver Heaviside solution. I didn't have the transformer in place. And of course most appliances have little motors in them, like blenders. You know, if you're running a little toaster, then it's not a problem. It's not an issue. You might burn up the heating coils maybe if your staccato wedges are too far apart, such as the voltage is peaking too much, too high. So there are different ways of raising. Let's go over the parameters now. The transfer coil is what develops the capacitive, the inductive capacitance that's going to create the surge. I said capacitive reactance, didn't I? But it's of the variety of capacitive inductance because it's a coil. And now I've created this habit pattern of the latest circuit to fashion or design the transfer coil to be the same inductance value as the two current coils. What was it? 2 microhenries. Now in the past I've done a circuit, I've raised the transfer coil to as high as 2.34 microhenries. I can't remember exactly the figure. Now when you raise the inductance of that transfer coil, you raise the power output of the device. It really surges. But it's at the cost of your frequency, I believe, if I'm not mistaken. The frequency goes down hill, and severely so, I might add. Now remember, we don't want that to happen. We want to keep the frequency up. When I talk about frequency, I talk about the staccato wedges, because we already know what we're inputting with the sine wave generator, but we're modifying that by creating these staccato wedges, and they have a frequency of their own, and that's what concerns me, because that's what I can see. The sine wave generator, I can't see that unless I narrow in my view and bother to look at it, and it's so teensy. The waves are so tiny. It amounts, because their power level is nothing. It's like zip, you know. It's so teensy weensy, because we're not giving this a whole lot of power. So why should those sine waves be any different? Their amplitude is going to be teensy weensy, so we don't care about that. See, the conventional view would be to look at those sine waves that we're feeding the circuit and worry about them, but we can't, because we're not feeding it a whole lot of power. We're giving it 3 volts, you know. It's costing us 12 volts to run the sine wave generator, but the sine wave generator itself is only putting out 3 volts. You know, if we pick up one of these sine wave generators on the internet, and I don't know if those are going to work. Those are digital sine wave generators. Are those sine waves good enough? I don't know. The simulator doesn't know the difference. It's putting out a pure sine wave, which for all intents and purposes is not digital, it's analog, if we compare it to the real world. So I don't know if a digital sine wave generator will work. You know, these are all questions that have to be addressed. We have to ask ourselves. When I worked on circuits, I took the Edison approach, because I didn't know what I was doing. I'm not Tesla. I don't have a simulator for a brain like Tesla had, if you read his autobiography. So I had to do everything Edison approach. I had to exhaust all options. And you know what? When you think you have exhausted all options and you're a complete idiot and a failure, that's when you're on the verge of discovering what you have overlooked. So not only did I have to exhaust all options in the course of the 3 years or 4 years that I've been studying this, but I had to exhaust my body and my mind to the point of collapse. And I had to throw myself on the bed. I'm telling you this for a reason, because you may have to go through this to succeed. I didn't solve all your problems. Trust me. I only took care of some of them. You may have in store for you a whole slew of problems that I never had to deal with, because I didn't bother. I just did simulations. And that's not to say you're not going to go through a whole bunch of problems I never went through. So I'm just warning you in advance. You may have to have a tremendous willpower and a desire to abuse yourself, literally, physically and mentally, to go through, regardless of the risks involved of the thing blowing up or boring you to shit tears, that it just sits there comatose and does nothing. It may also tax your body and mind to come up with, okay, what have I overlooked? Because this is what you have to keep asking yourself when you fail. Every time you fail, you have to ask yourself, you don't ever assume that it's a failure. You will want to think that. You will want to feel that. But you must tell yourself, I'm trying to give you a pep talk for a reason, because this is more important than anything else. You have to tell yourself, program yourself, every time you feel or think that way, no, what have I overlooked? What have I not thought of? What am I missing? What am I dumb about? Too stupid to notice or think about. And you've got to answer it yourself, because no one's going to be able to help you, not even me. I can try, but there's no guarantee I'll be able to. You're the one on the scene with your guardian angel, and we all have a guardian angel who's out there to help us. With your guardian angel and your soul acting as intermediary between your guardian angel and yourself, and it's your guardian angel who has all the answers, and your soul who can access it and share it with you. Act as the portal between you and your guardian angel, and it's between you and your guardian angel. It's between nobody else. You know, our life is based on developing our relationship with our guardian angel through our soul. And as we develop that relationship, we reach godhood status eventually. But it also is the methodology behind solving problems. And as Charlie Lutz said, the only way to survive in the Aquarian age, this upcoming age, which has already kind of started gradually, and is warming up. You know, it started with the freeing of the slaves, Lincoln freeing the slaves, and it was planted 2,000 years ago with the crucifixion of Christ, but it's not really warmed up yet. It's got a ways to go. It's got a few hundred years to go, or 100 years to really kick into full gear. But be that as it may, survival in this Aquarian age is based on intuition, based on our rapport with our guardian angel, our higher self, if we want to survive. It has nothing to do with spiritual growth. It will be, the consequence will be spiritual people who will survive, because it'll be that kind of relationship that makes it possible to survive and also solve physical problems, such as how to create an over-unity device. So it's between you, yourself, and your I, not my I, that you will solve these problems. It's, you know, the way Iasos, IASOS.com, you know, he creates this celestial music. It's totally a self-involved project of his, and his relationship with higher beings, you know, celestial beings that feed him this stuff, and he comes out with this beautiful music. It doesn't involve anybody else. He's a one-man band, and that's what you have to look at this problem. I can start you off, and I can advise you from a remote distance, but I can't solve your problems. Ultimately, you have to be the one to solve your own problems. So I'm telling you in advance, you may have to go through the Edison approach, because that's what I've had to go through, and literally take yourself to the point of tears of exhaustion, because you think you've tried everything and exhausted all options, and yet you're on the verge of overlooking one option you haven't tried yet, and that might be the one that gives you success if you bother to go the extra step. Yeah, I'm telling you in advance, it's cruelty to go through this, but somebody got to blaze the trail, and if it turns out to be you and I, then so be it. But nobody else seems to be interested for the most part. A few people have, and if they've succeeded, they keep, you know, it to themselves. There are a few people on Energetic Forum who've commented that they have succeeded, and some share it, like Mark Belanger, and some do not much. They say, well, I do it at home and for my neighbors, and that's all I do, you know. So this is all I can do, is design it. I can't even build anything, but I've already covered that in prior videos, so I'm not going to cover that now. Anyway, so there's a lot of exhaustion involved. And then there's going to be a lot of servicing. I don't have to service my circuits, right? I run them in the simulator, and I don't have to worry about it, because they don't break down. But the physical world's a different matter, and you're going to have to service and maintain, so I've already covered that. Okay. So we covered exhaustion, we covered servicing, we've covered the staccato wedges that have to be compacted. I don't compact them when I simulate them, but you will have to. You'll have to raise the frequency, and there are different ways of doing it. So by lowering the transfer coil, you're going to raise your frequency, but you're going to lose your power. So you may have to raise the frequency of the sine wave generator. That's one way to do it. Now I should have maybe, but I didn't write down all the notes to myself about all these different factors, so you may have to play around with them and rediscover what I've chosen to forget in the course of developing the circuit, because actually it's more important than the circuit is the skill involved of becoming familiar with all the different parameters of all the different components. And when you change one, what happens? What are the results? So you may spend most of your time in the beginning toying with the thing to see what happens. Now in the simulator you find out. In the real world you may not. It may either explode or just sit there comatose. And in between, you know, if you have a lot of test equipment, that's good. That's more power to you. If you got the money to spend on oscilloscopes and you know, all these different measuring tools, or what are they called? They have the ring around them. You put them around a wire to measure the amperage or voltage without having to connect directly to the wire. You know, you buy them at the hardware store or whatever online. You know, all this costs money, and so having test equipment is good. There's nothing wrong with it. My simulator is my test equipment because the simulation is the test. is the test equipment. So I don't have to buy the test equipment because the simulator provides both the circuit and the test equipment all rolled into one, and I don't have to even buy it. I do it for free, so long as I keep everything simple. And, KISS, keep it simple and sweet, short and sweet. But it's going to cost you a lot of money on test equipment, and it'll pay for itself if you get the basics, Don't go all out and buy what you don't need, but do know what you're doing while you're doing it. Keep an eye on everything, because when you see your test equipment giving you data that's undulating, and I'm telling you this because Nelson Phillips saw the same thing happen when he was in charge of setting up PA systems, public address systems for rock concerts. And when he learned after 10 years of experience, when he sees the dials on his meters wildly undulating up and down, and the undulation widen, going higher and lower, I've seen this happen, the thing's going to explode. It's warning you in advance. So that's the value of having test equipment, is you may get a little warning window of about a microsecond or a fraction of a second, or maybe 1 second or 2 seconds, to shut the thing down before it explodes in your face. I want to tell you, not that I'm trying to be cruel, but I am trying to frighten you for a reason. There was a Life magazine article back in the 60s. Somehow, I don't know how, I can't remember, this Vietnamese person, this is concerning the Vietnam War, he somehow got a grenade stuck in his body. I don't know how he managed to do that. And I can't remember if the pin had been pulled already. It might have been. Yet, because of the compression of his flesh, the plunger or whatever, the handle, had not been released, and so it didn't go off. And the surgeons there, the American surgeons, were trying to extract the grenade from his body without allowing the grenade to explode. And they did a slew of pictures, one in particular, it's burned into my memory. They put sandbags around the guy's body on the operating table, and they had holes to stick their hands in to operate on him to extract the grenade. They succeeded, but of course they had the risk of losing their arms and his life if the thing should have exploded in the course of extracting it from his body. But that's literally what we're dealing with here. We're dealing with a bomb that could go off. And so it would be a good idea to put a wall around this circuit and an enclosure maybe on the top whenever you turn it on to run it, because it could blow up. And it could be a mess of a job cleaning up your shop, let alone the hazard it might pose to yourself if it should explode. And I worry about these things because I've been electrocuted, so I know what it's like to have seen these circuits blow up on the simulation safely and not injure me. In the beginning, when it first happened, when I created a surge back, it was March or February 25th, 2017, I panicked. I panicked so much I couldn't even think to turn off the computer because I didn't know how to turn off the surge. Because when I turned off the circuit, the surge sped up. This is the funny thing about surges that conventional wisdom does not understand. Voltage suppresses a surge, and that's why I feed it so little. Because if I fed it more than 3 volts, if I'm going for the full Monty, the full circuit to supply lots of power, I can afford to give it 3 volts. If I'm doing a table model, I can't afford to give it more than a few microvolts, because anything more than a few microvolts, even millivolts, kills the darn thing, and it won't surge on me. So I have to throw away. I have to use a voltage divider. If you've read my book, you'll know that in there's chapters devoted to that early on. It's called the table model, the solution chapter, in which I cover that. I cover a proof of concept because you really can't get anything useful out of it because it doesn't have the Oliver Heaviside additional feature to it. All it does is create surges, and maybe you can light light bulbs, okay, but you won't be able to rotate. You won't be able to power an inductive load. I I almost said rotate a motor, but none of these can rotate a motor. I've already come to that conclusion. It's worth repeating to remind myself this darn thing cannot rotate a motor, so it's not a motor. It's simply a solid-state generator. Be that as it may, I did do a scaled-down model, and it's complicated, and it turned out to be what I had to do for the Heaviside solution. Namely, you put a capacitor in parallel with the spark gap to stabilize the spark gap's firing, because you want to make sure that spark gap fires. And if it fails to fire, then the whole thing explodes in your face. So the spark gap is there as a safety feature. Now you could run a clock timer with a mechanical relay to open and close the switch to short out or somehow ground out the energy of the circuit momentarily in a rapid fashion rather than use a spark gap, but I don't think a mechanical switch will switch fast enough. And there are dangers involving spark gaps whether or not they fail to fire. I've read that. So there are all these risks that I don't know how to solve. You know, I've taken the easy approach and said, well, I'll just use a spark gap because it's more likely or less likely to fail to fire than a mechanical relay. But that's not to say that you may not have problems with a spark gap, and that's would be the first thing to service when you look at servicing and maintenance of this kind of circuit, is to look at the spark gap, and maybe you just replace it. You know, a lot of this is trial and error, unfortunately, and maybe some components like the spark gap you just replace on a regular routine basis regardless of whether or not it needs to be replaced. You just replace it anyway because you don't want it to fail, because if it fails then the circuit blows up. So that spark gap is there not to create energy. You know, everybody says, oh, Tesla spark gaps create free energy, radiant energy, and you know the Edwin Gray motor was based on it, and Peter Lindemann did a false analysis thinking that that was the case, that the spark gap was there to generate energy. I don't think so. I think it was there to dissipate energy. In fact, I think the Edwin Gray motor is very much like my circuit device, because if you look at the Edwin Gray patent, you will see a 4-diode bridge in there in parallel with what looks like the load. And so it looks like it's very similar to my circuit. It's different, but it has similarities. And so I don't think the spark gap has anything to do with radiant energy, you know, John Bedini, and you get the screen, the copper screen to collect the radiant energy. That's a bunch of hooey. It's to throw people off. This is Mark McKay's analysis. It's very good to read these things. Mark McKay did a thorough analysis, and I've zipped up all the files on one of my blog spots. If you go to any one of my blogspot.com blogs, Define the Atom is one of them. So that's the one I remember. I think spicysurges.blogspot.com is another. And then go to my profile, and then look at all the different blog sites I have. One of them I think is called Am I a Raisin Head, which I misspelled raisin. It's supposed to be raison, you know, the French reason. Am I a reasonable head? It might be that one, or it might be another one, Tesla, I forget, that has the article, that has the link to my Google Docs zip file. It's like 40 megabytes of all the different files that Mark McKay put out on the internet analyzing the Edwin Gray motor, and it's very good reading material. So what was I made a tangent. What was I going to say about Mark McKay? Oh, that the spark gap and the copper screen around it was all meant to foil people into thinking that that was the power source. It's not. It was meant to distract people. But it is a dissipating device, at least I suspect. That's my opinion, because that's the way I use it. And so I in a lot of my diagrams in my book, I do say put a nested Faraday cage around it, because according to Byron Brubaker, you're going to get rheumatism from all the microwave radiation coming out of that thing as it fires, at the very least. And if you ever plan on having children, you'll have mongoloid children, because the Army already, according to Dr. Robert Otto Becker, who wrote the book The Body Electric, the Army tested microwave radiation beamed at their helicopter pilots' genitals their whole body, but including their genitals, and it increased their risk of creating mongoloid children. And so this idea that, oh, older fellows are more likely to have mongoloid children has nothing to do with age. It has to do with microwave radiation over time. That's all it is. And so you want to shield yourself if you want to know what's good for you. So the way, and then I spend a whole chapter in my book dealing with EMP attack. You know, the grid is susceptible to EMP attack. And so this guy wrote a book, he wrote a book, and then he's got a web page, and so I link to it because he goes through all the procedures of how to protect your devices properly. And you don't try to ground it, because that's just, if you don't know what you're doing, you could make things worse. You just try to do alternating layers. You know, the spacesuits of the NASA astronauts are made with alternating layers of foil and paper, many, many ply of that, plywood is made of a composition of alternating layers, and then you repeat those alternating groups. And that's the way the spacesuits are, and that's the way an orgone blanket or an orgone box or an orgone wrap is done. You know, Wilhelm Reich, you do alternating layers of conductive fabric versus insulative fabric. You know, wool versus sheep's wool versus steel wool in the case of orgone blanket. But in the case of an astronaut's spacesuit, it's foil and paper. And in the case of let's say protecting our electronic devices from an EMP attack, it's foil and paper, although I like to combine paper with plastic. Actually, that was the advice, was actually foil and plastic, but I found that plastic sometimes has sharp edges, so I have to use paper with on either side of the plastic to shield the foil, so that you can't afford to have any breaks, any holes in the foil. So I use paper to protect the foil from the sharp edges of the plastic. But since the paper and the plastic are both insulative, that's one group, and then you alternate with the foil back and forth as you make your layers, and you don't ground anything. You just make all these layers, and I have my computer hard drives wrapped that way, and that's the way you protect your spark gap component, so that you shield yourself. It's already got ceramic around it, but that's not enough. That's just one layer of insulation. There's no foil there. I don't know what's underneath, but you need multiple layers to shield yourself, and about 3 or 4 ply will do the job. When it comes to orgone wrapping, they say 7 is the max, and 3 or 4 is usually optimal when you're doing numbers of plies of these sets of layers. So that's one concern, but that's the only purpose of the spark gap, is to make sure it doesn't surge to infinite oblivion and blow up. So you have to make sure that thing fires, and so that's the purpose of the capacitor connected in parallel with the spark gap, is to ensure that you get a storage, because capacitors can regulate frequency, because they charge and discharge, and so when having a capacitor in parallel with the spark gap, you ensure that the capacitor will charge and discharge at a specific rate, and that helps ensure that the spark gap fires at a specific rate. Now, I've gotten away without it, but not all the time. So it's just a good measure of protection to make sure you put one in there, and then pick the right value of that capacitor to go with the spark gap to produce the firing at the rate that you want it to fire at, to get those staccato wedges at the right frequency that you want them to be at. So this is all like tuning a violin or something. You've got to tune all these things. So that's one thing to worry about. Now, the 4-diode bridge is necessary because you're building up voltage. See, it's a very interesting device. Let me pause for a minute here. So the transfer coil initiates the surge because of its capacitive inductance relationship with the voltage coils. Now, the voltage coils are connected in line with the spark gap, the 4-diode bridge, and the capacitor on the far right of the circuit diagram. All of that builds up voltage. and it's a step-down voltage transformer arrangement in the relationship between the voltage coils and the current coils. And that creates a division, a segregation, so that voltage builds up in that area of those components and current builds up in the area of the current coils. And the current coil's job is simply a place for the current to be. They don't create the current necessarily, they just serve as a transformative element, shall we say, because of their relationship with the voltage coils. All four minimum, coils are on, these are solenoid lumped inductors. They're on this iron stick, this iron rod, with a 99% coupling coefficient, and for some reason, my God, I tried 98% and it failed me. So somehow or another, you've got to get the coupling coefficient on these four coils really, really high, just there at unity. Now the simulator won't let me go to unity, it craps out, and that's the way it is with simulators. So for all intents and purposes, it is unity. And so, if you've got a 7,000 to 1, ballpark figure between your winding ratio of number of windings on your voltage coils versus the number of windings on your current coils, you've got to get a coupling coefficient there at unity. That's not going to be easy with that much of a distinction between the numbers of windings between those two sets of coils. And that's going to be a problem to overcome. So you can use the facility, the advantage of making these solenoid coils, not air core coils, because you're going to the only way to get it up to 99% is to put it on an iron rod to get the take advantage of the magnetic transference between the four coils in the center of the coils, where the magnetic field is the most intense. That's where we put our cores, right? In the center of the coil, to where the magnetic field of the coil is the strongest. But that's where we're going to be transferring the magnetism among the four coils to get them to share at unity coupling coefficient. It's not going to be easy, but you're going to somehow have to do it, because 98% won't do. The simulator just craps out and goes comatose. Doesn't explode, it just goes comatose. So that's a problem for you to overcome. Now, whether or not that core of those four coils should be a toroid, now we're getting to somewhere. Now, I would imagine a toroid is ideal. In the simulator, it makes no distinction. The only distinction I get to make in the simulator is the coupling coefficient. But how do we achieve that when we build it? I think a toroid is the only way to go, because that comes out of Edward Leedskalnin and his perpetual motion holder. And that gets into another chapter in my ebook on the material of construction of the armature. I deal with that, and I spend a whole chapter on that. It's not long. My chapters are not big, as you've probably seen. But I do mention Edward Leedskalnin because it's pertinent. The material of construction of that solenoid core, of those four solenoid coils sharing the same core, should be the same material of construction, probably, not as modern day transformers, because that's the Oliver Heaviside transformer section of the circuit, that's something else. It should instead be the material that is used for a perpetual motion holder. It should be able to retain magnetism. And that's probably the only way we're going to get 99% coupling coefficient anyway, is for the magnetic field to be retained in that core, that solenoid core, that's going to build up all of this negative power factor energy of splitting, separating the voltage from the current by half a cycle, half an AC cycle, 180 degrees phase shift, is probably due to memory. And that's not the way people do things with transformers. I learned the hard way. When somebody sent me a transformer, it crumbled. A few of them, he didn't pack it properly, and some of them broke, and it was very friable. And the core material is actually a composition of iron and some other substance holding it together. And it just fell apart in shipping. It banged around inside, and because he didn't put any packing material to speak of. A little bit, but not a whole lot. Certainly not for the transformers. He put a little bubble wrap around some of the vacuum tube capacitors. Some of those broke anyway, but some of the transformers broke because they weren't packed with any packing material at all. And that's when I learned, and then I did a PMH experiment, a perpetual motion holder experiment involving those transformers, and I learned very quickly that the minute you take the electricity away, the perpetual motion holder falls apart. It doesn't hold together. And it took me a little while to figure it out. Oh, it's not an iron rebar or an iron bar you buy from the hardware store and bend into a U shape, and then you get a solid plate of iron to pose as the feet, and you sand everything down to a smooth surface so that you have maximum surface contact between the feet of that U-bar and the bent U-bar that you made and the plate to form a ring, a toroid, a magnetic toroid. If you don't use solid iron, you know, you're not going to get retention of magnetism, remnants. Magnetic remnants. You're not going to get that. And I spend a whole chapter in my theoretical book. That's another good one to download, the theory book, because I talk about the computer memory between 1955 and 1975 and how that was fashioned, how it was built. They had ferrite rings threaded with wire going through them. And that's how computer memory worked during that 20-year period. And that's the kind of situation we want to have in our solenoid coil. We want to retain magnetism and remember it because we want it to build up between cycles. We don't want it to lose magnetism between cycles. We want it to remember that magnetism and build up, or else it's not going to build. We're not going to get a surge. It's going to be comatose. Trust me. The amount of energy we're feeding this thing is going to dissipate so rapidly. If we don't develop a surge, it's going to go comatose on us. It's going to follow the laws of thermodynamics because it's not going to have these added advantages to create a surge and create overunity. It's going to follow conventional wisdom instead. So we're fighting thermodynamics is what we're doing. And we have to fight it per rate, per unit of time at a certain rate in order to get over unity because we're constantly, it's like having a bucket with holes in it. We got to feed it so much water per unit time in order to make sure it remains full of water at all times because it's busy leaking constantly. You know, that's the fighting deal we got to deal with, including, you know, making sure it doesn't go comatose, you know, leak out all its water or blow up and have too much per unit time. Everything is per unit time. In a framework of time. Okay, so now the transformer is a standard transformer. It's going to lose energy. You know, it's got magnetic hysteresis and whatnot, but it'll make inductive loads possible. And that was the heavy side solution to the last bit, the last chink in the puzzle for me to solve. But it's going to be your standard transformer components, so don't worry about that. It's the solenoid you have to worry about. So it's probably going to have to be a toroid and probably the solenoid and probably made out of solid iron. And it's I've wired toroid cores before, and it's a lot of work. Oh boy! Now I've inspected, you know, an AC motor, and I realized they did things the easy way. But that's because they could do welding. If you can do welding, you're a step ahead. Because then you don't have to deal with a solid toroid. You just put your windings on a bobbin. You slide your bobbin on one half of a toroid, you know, that's outfitted to receive it. So your toroid is not a circle. It might be a U shape, you know, let's say. Yeah, a U shape turned sideways. Not a C, because that's round. But a U turned sideways on its edge is like a PMH experiment, a U. And you slide your bobbin on one of the feet, and then you might slide, you know, that might be one voltage coil, let's say. I don't know what's optimal. You may choose to wind both voltage coils together on the same bobbin. Maybe that's optimal. I don't know. Or maybe you might want to distribute it evenly and put one voltage coil on one U leg and the other voltage coil on the other and just, you know, link them together because they're supposed to be linked together. They're supposed to be shorted to each other. They're supposed to be a closed electrical loop together. Be that as it may, maybe you'll find it's best to put them on two different bobbins. But if you have welding capability, then you'll be able to have this U, rebar or whatever that you've bent into a U. You put your two voltage coils on the two legs, and then you can wrap your two current coils, one on one bend of the U, prior to your, actually, in between your two voltage coils on the bent part of the U, you'll do your minimum two wraps for your current coil, because that's the minimum for a current coil, is two wraps, two windings, two turns. So that means your voltage coil, according to the simulation, will be 14,142 turns or windings on each of those two voltage coils in order to be 7,000 to 1. Because it's 7,071 was what I computed. So in the ballpark of 7,000. But if you're going to do two wraps on the current coils, that means 14,000 on each of the voltage coils. So you've got your two wraps of the current coil on one current coil on the bent part of the U, and then you slide in the two voltage bobbins, and then you weld the other U arm, shall we say, the bent piece, to the other piece to make a toroid, and that other U-bar piece has the other current coil wrapped twice around it. And so now you'll have your toroid, and you'll have a solid magnetic connection, and it'll probably help achieve a coupling coefficient of unity among those four solenoid coils. It'll probably help a lot. Now I'm thinking to myself, that might be the only distinction between solenoid coils and transformer coils is the composition of the core material. Because up until now I couldn't imagine what the difference is, and the simulator knows there's a difference. And the transformer in the simulator actually loses energy. I can see it happen in front of my face, while the solenoid coils do not. So I think what's happened is the simulator, the designers of the microcap simulator knew to put in remnants in the lumped inductor model for the solenoid coils in my simulation, while in the transformer they put in the compositional material for the core material, and so it loses energy. I don't know why that's better, in terms of the heaviside solution, but that doesn't create energy. That loses it, and so it helps us spend it for an inductive load. But here we're still focusing on the left side of the circuit that builds up the surge. And so for that one we need solenoid coils, but it probably needs to be on a toroidal core. So now that I've covered that, let's see what else is there to cover. Now the capacitor in parallel with the spark gap, I have it at a high rating. I have it at 1 millifarad. I couldn't take it any higher. The simulator would give me error messages, or it would fail to surge. The spark gap would fail to fire and it would blow up or something, So don't look to take it any higher. You might be able to take it lower. You might be able to take it as low as the capacitor to the right of the 4-diode bridge. Now the capacitor to the right of the 4-diode bridge is at 1 picofarad. And that one has to go down lower. See, when you raise the capacitance of these two capacitors, you raise your power level, but you also run the risk of the spark gap not firing, especially in particular the capacitor in parallel with the spark gap. So you don't want to raise that one too high. But I got simulation errors that told me that the simulator was having trouble simulating, which might mean that the circuit is failing to properly behave. In the real world, it might be the case. If I did not, for instance, lower the capacitor to the right of the 4-diode bridge low enough. So I kept lowering it, and by factors of 10, and I kept thinking, shit, how far do I got to go? Because I had it up as high as the other one. I had it at like a millifarad or something. Well, it wasn't until I got it down to a picofarad that the circuit functioned properly. So you might have to lower it less than a picofarad. And if you can't buy anything, it's possible to make your own capacitors. I've done it. I don't know how safe it is or how usable, but I've for bionic circuits, I've used glass plates and aluminum foil, and I devote a little bit in my book about that. How do you make a mirror? You know, it's how do you make a capacitor? Not much different than making a mirror. You just silver both sides. You know, I believe they use aluminum, and you electroplate one side of a glass plate or a glass pane with you know, a fine layer of aluminum, because you've electroplated it basically, and that creates a mirror. But to create a capacitor, all we have to do is mirror both sides, and now you've got your own capacitor. But with one added distinction: you've got glass, which is a beautiful dielectric. It can't take high voltages without cracking and breaking down. You know, it's not maybe a perfect dielectric material. There's probably better ones that can handle high voltages, but perfect in the sense that, well, I don't know, it may not be perfect, but in terms of it's only good in one sense, and that it's thick. Glass comes in very thick, but you can get plastic thick too, you know, and make a polyethylene capacitor. You may have to make your own capacitors. And I remember some people on the internet saying sometimes that's what you have to do. When you craft a circuit, you have to make your own capacitors. You already have to make your own coils, except for the transformer. That you can probably buy and just use off the shelf. But if you don't want to wind, you know, a 10 Henry transformer on both sides, like my simulation provides or requires, in order to get the inductive load section of the circuit up, you know, the branch that has to do with connecting an inductive load, it requires the use of a transformer at 10 Henrys on both sides, a one-to-one relationship between the primary and the secondary, the inductance relationship, not the coupling coefficient. Well, that one I had to have high anyway, but the ratio between the inductance of the two coils was 1-to-1. Now the left side had to be high. The right side could be low, but there's no advantage to it, and so I just made it 1-to-1, and that seemed to be the only way to go, really. I didn't bother trying to raise the right side, so I don't know what would happen. You know, the secondary side, the output side, I don't know what would happen. But I just kept it 1-to-1. So you may just buy the transformer, but meanwhile you're making your solenoid coils yourself, and fashioning even the core, for that matter. And you may have to make the capacitors yourself. I don't know. Or you may be able to get by buying them off the shelf. It all depends what kind of parameter you have to deal with. If you got to go less than 1 picofarad, you could get away with, you know, buying 10 1 picofarad capacitors and stringing them in a series to get 1/10 capacitance out of the entire string of inline, you know, series capacitance. You know, 1/farad plus 1/farad 10 times, to get, and then the reciprocal of that. You know, it all depends on what you know. This is all up to you. Now, I used a ceramic capacitor as my model because I didn't need to raise the equivalent series resistance of my capacitors. But there are exotic materials for dielectric, for the dielectric of capacitors. Tantalum, even aluminum, weird, aluminum oxide, and that brings up the equivalent series resistance, but it only got in the way. Actually, it turns out I just need a very low equivalent series resistance, and it's better for the capacitor. I've read articles which says when the equivalent series resistance of a capacitor is high, the capacitor tends to overheat, and when it heats up over time, it'll stress the dielectric and cause puncture holes through the dielectric, and of course that shorts out the capacitor and makes it useless. Especially since we're feeding at high frequency, or moderate frequency I should say. We don't want to stress it any further than we have to. So it would be good to choose capacitors with a low equivalent series resistance so that you'll have less maintenance. So that's another thing you might have to swap out on a regular basis, regardless of whether or not it failed you yet, because it may be already cooking. You may look at it and it looks like it's been cooked a bit, you know. So you may have to have a blower arrangement blowing air through this thing, through this circuit, to keep it cool, you know, because you may have a lot of components heating up, coils and capacitors heating up. it certainly, again, going back to Mark McKay, that's how Richard Hackenberger solved the problem of the FCC coming in, and that's another problem you got to deal with. Your circuit may create radio interference, so you may have to run. It's a good idea to run a little AM radio nearby as you, anytime you turn your circuit on, to see if you're putting out any kind of electrostatic or electromagnetic interference into your local environment, because if you get the FCC involved, they'll come in and take everything, including your toothbrush. They won't leave anything behind. They're nobody to mess with. They're worse than the DA's office. When they raid big time, and you don't get anything back. So, you know, you'll want to run a little AM radio to make sure you're not putting out anything, because if you are, it'll be a good idea to blow air through your circuit and get rid of it, to move, because you'll be ionizing air. You know, as you build up an electrostatic charge, because if you're dealing with high voltages, you're going to be building up an electromagnetic field and an electrostatic field. And if it's severe enough to create radio interference, you're going to want to dissipate it. And one way to dissipate it is to ionize. It's going to ionize the air automatically, but you'll want to move the air out of the circuit so that fresh air comes in. And when that fresh air soaks up some of that ionic charge, or some of that charge ionically, in an ionic fashion, as it keeps moving, it moves some of that charge away from your circuit. And the ionized air molecules will meet up with various objects that are grounded to the earth, such as walls of buildings and whatnot. And so those ions will ground themselves. But if you keep the air moving through the interior and possibly the exterior, mostly the interior is where the intensity is going to be, then you can move those ions, and thus, by transference, move the electrostatic charges that those ions carry out of the interior of your circuit into the surrounding space in your lab or wherever you choose to run the circuit, outside or inside. And that'll help convert the electrostatic charge component of both the electrostatic and electromagnetic buildup of your circuit into ionic charges, and thus keep the FCC happy, keep your neighbors happy, and keep everybody happy, including you and your circuit, because your circuit can't really afford to build up a charge. You know, a simulator doesn't build up anything. It builds up numbers is what it builds up, but there's no residue to build up. There's no environmental hazard that impinges on the circuit to stress it further. Now remember, one of the last videos I just did was on the self-accelerating nature of a peroxide breakdown. When temperature builds up that cannot be vacated, it accelerates the breakdown of the peroxide. Well, lo and behold, the very electrostatic and electromagnetic field that surrounds these surging conditions are what's contributing to their acceleration, but will also contribute to the FCC stepping in and calling quits to your nice little hobby. So, on the one hand, the environmental surge is our friend, but sociologically speaking and legally speaking, it's not. So again, there's another little juggling act we have to give up. We have to sacrifice some of that environmental surge, that environmental condition, in order to maintain the hobby of experimenting with the circuit. Because, you know, the simulator doesn't give us that. The real world will. So let's see what else to cover. Trying to cover everything. Oh, now Mark McKay told us what was fashionable, and you know, Tesla didn't invent it. He kind of came up with his own recipe, but it was kind of popular in his day. What recipe to use to slather over your coils to seal them. Now you're going to have to seal everything, because you can't have any arcing, because it's going to want to arc at those high voltages. It's going to want to arc. You know, it always looks for a way to arc to neutralize the voltage buildup. And so all of your solder joints, and that's another topic I have to cover, soldering versus welding. We already covered that for the toroid, but we have to cover it for the wires as well. Your circuit may not work because of the solder joints alone getting in the way. Somebody on the internet said he can get his solder joints down to 100 microohms of resistance, and that's pretty good. You may want to measure practice on some wire connections, solder them, and see what is the resistance. Measure them, and how much do they vary? Because anything more than 0 is going to create problems within the current sections of the circuit, not in the voltage section. So that's why I brought that up initially, another reason, and it's good to finish that thought off. In the areas in which voltage builds up in the circuit, we want resistance because we want voltage to build up. You know, that's the voltage coils, the spark gap, the 4-diode bridge, and the capacitor to the right of the 4-diode bridge. We want voltage all along that linear arrangement of components, but we don't want it anywhere else because, well, on the left-hand side of the circuit, the power side, the build-up side. Because if we have it in the area of the current coils, it's just going to get in the way. It's going to kill the circuit. It's going to kill the surge. So wherever we have connections there involving the current coils, you know, the wires feeding the current coils and the current coils themselves, we can't have resistance to speak of. And that might mean you either have to, and I cover this in my ebook, you either have to weld the wires connections to the components, or you have so many wires soldered in parallel as to make it look like spaghetti. And Eric Dollard actually did that. In one of the old 1980 decade Borderlands videos, Peter Lindemann spends a good deal of time in front of the camera sitting there talking about Eric Dollard's wireless transmission of power experiment, and he talks about the aerial, and it's a pancake coil with spacing between the wires. It's a great video to look up on YouTube. I linked to it, but I can't remember offhand, you know, what the link is, so I can't tell you offhand. It's a great video, and if you look at some of the close-ups as Peter Lindemann rotates the antenna around in different directions, you'll see there are multiple connections between the aerial and the coax that they use to connect to the aerial. The junction between the coax and the aerial are actually many wires that are heavily insulated. They're not magnetic, you know, coil wire. They're, you know, I don't know, but let's say gauge 16 wire or 12 with, you know, a lot of insulation on them, and there are a lot of them. There's like 2 dozen or 3 dozen wires, all of them in parallel, and that's to reduce, because they didn't weld them, they had to solder them, and those solder joints are giving you resistance, and he didn't want resistance, obviously, or else he would. I wondered about that when I saw it, but now I understand why he did that. Because solder joints offer resistance, and wherever your circuit can't handle resistance, that might be one thing you have to do. You may have to bundle a whole bunch of wires in parallel to overcome not the resistance of the wires, but the resistance of the joints, the solder joints themselves. Because you know what happens? It's just like capacitors in series. If you get resistors in parallel, it's again a reciprocal relationship. You know, you take the inverse, the reciprocal of each resistor, and add it together and take the reciprocal of that, and you end up with a nice low resistance, total resistance, just like you did with putting capacitors in series. You do with resistors in parallel. When you want to lower either one, you know, lower resistance, overall resistance versus lowering overall capacitance, you may have to do these kinds of juggling acts to accommodate, you know, what do you get to buy, what's available, versus also what you get to do putting things together. You know, do you have the ability to weld wires together? Will it work? Is it workable? I don't know. I've never done this. So you may have to solder bundles of wires together in parallel. You know, it's good to know that the Tesla Motors, you know, the company who makes the Tesla car, I can't remember if it's the rotor, I believe it's the rotor on their motor, has thousands of wires in parallel, thousands. And they get the amperage up to kiloamps, and their voltage is around 300 or 400 volts on that motor. Now, Sangulani Maxwell Chikumbutso of Kenya his over Unity device, he gets it up to kiloamps, and his voltage is down a few hundred volts, I believe. It's not a lot. So he has the amps up pretty high. Now how else are you going to get the amps up? Unless you've got wires in parallel, you know. I don't know about Chiku, Max Sangolani. I don't know about him, but what we do know, because he doesn't tell us too much about how he constructed his device. He just tells us the output, you know. But with Tesla Motors, somebody did share on the internet how they, a little bit of the construction details of the motor, because, you know, Tesla Motors doesn't tell too much either. But he did share with some people that I believe it's the rotor, the coil windings is literally, if not hundreds, if not thousands of wires in parallel. And it makes the motor quite large, but apparently they have to get the resistance down on those wires for some reason in order to get the amps up. For some reason they wanted the amps to be high, and that's how they did it, by having a large bundle of parallel wire connections on their coil. On their coil they had a lot of. So whereas I get by on my simulator with a minimum of 2 coils each, 2 voltage coils and 2 current coils, in reality you may have to do a lot more than that. On the current coils, that's where you have to add in your extra coils, and you get more power. I don't do it because I don't need to, and because my simulator won't let me. But I have done experiments just focusing on that area alone, what will happen when you alter the number of parallel current coils and parallel voltage coils, you know, that are connected in parallel in each set. And it actually increases your power. So I went as high as 8 current coils and as high as 3 voltage coils before the benefit started to trail off. In other words, each time I added a coil past that point, I didn't get as much benefit as when I added the previous coil. So I stopped. I figured, well, 8 current coils and 3 voltage coils seems to be the maximum efficient number of parallel coils, but that doesn't mean it's going to be that way in the real world. You may find you need to add 20, 30, 1,000 current coils in parallel, because A, the resistance is going to have to be very low, and B, it's somehow, well, because that's current division, right? So again, that's one of those laws of electrodynamics. When you have current division, you actually increase your current. And you want the current to increase, and that's the only way to do it. So with the voltage coil, you want a bigger coil. You still have to have a minimum of 2 each for the surge to be able to develop properly, or at all. But how many coils beyond 2 is another matter, and that's going to be up to you to find out. But the only way to increase voltage in the voltage coils is to increase the inductance. The only way to increase the current of the current coils is to increase the number of coils, because there's going to be a limit to how far down you can reduce the inductance on those current coils. And any further, you're not going to be able to take it. So the only way to take it any further, the current, because again, this is a step-down voltage transformation situation between the voltage coils and the current coils. So the only way to maximize your current in the current coils, which again is going to feed back and maximize your voltage on the voltage coils, if you can increase the current in the current coils, that increases the voltage on the voltage coils. So although we call it step down or step up, it's really bidirectional, because in a transformational situation, even though these are solenoid coils, regardless, in a transformational situation of step-down, step-up transformation, it's feedback, and it's constant feedback going back and forth. And so we want to maximize voltage on the voltage coils, we want to maximize current on the current coils, and there's 2 different ways of doing for each one, because they're 2 different situations. So for the voltage coils, we have to increase their inductance, their individual inductances, but on the current coils, we have to increase the number of current coils that are connected in parallel, because that's current division, and that'll increase the current in that section of those solenoid coils, and that'll help increase your power output, your power surging. A lot of little details. Okay, what else? Now your switches, your on-off switch. Now I looked on eBay, and there's actually a knife switch designed, for the intention of high voltages. And it's a heavy-duty knife switch, let me tell you. It's no small knife switch, one teensy little, Heathkit, knife switch. We're talking heavy-duty with plastic all over everything and huge. And it's for safety's sake. Maybe you need something like that. I don't know. It's things to keep in mind. And then when you get your spark gap, how much voltage can it handle? When I looked into my simulator to see what was going on, inside the spark gap, it was gigavolts, literally. And so when I looked on eBay for spark gaps, obviously, they're not designed to handle gigavolts. You're lucky if you get maybe 6,000 volt tolerance on a spark gap. So you may have to go for a spark gap with the highest tolerance. I don't know. And I also, the simulator did not allow me to simulate more than one spark gap. I would imagine they have to be in parallel, but then that might prove fatal because then they'll be firing at different times. In series may not be any better. Well, no, in series may be the only way to do it because they have to fire at the same time. So anyway, the simulator didn't let me put in more than one spark gap because the simulator limits me based on number of components and number of nodes, the node being the voltage barrier between one particular area of the circuit and another. In other words, the circuit is a voltage gradient map, and depending on how the voltage distributes itself, based on how you've constructed your circuit, will determine where the nodes are. But the node is like a barrier between one voltage area and another. And so it limits to me to so many nodes and so many components. And it has some way of computing it. I still haven't been able to figure it out exactly. But it tells me when I've reached my max, and then it doesn't get to simulate. And it shuts down. It doesn't even turn on. It doesn't even simulate. So it doesn't let me add more than one spark gap. Why? Because when you look inside the model, the simulation model, the macro model of a spark gap, it ain't one component. It's like a dozen different things: capacitors, resistors, inductors, and grounds, and voltage sources, and so many different things operating that one spark gap in the simulator. Now, when you go and build it, it's just one component, one spark gap, and you throw it in there. But with the simulator, it costs me a lot of components, and it builds up a tremendous voltage. So I don't get to do more than one spark gap, but you may have to put in more than one to be able to handle the voltage. So, like any battery or resistor, well, let's look at it, use the battery as an example. If you have two batteries in series, that cuts the voltage load on each one by half, or doubles your overall voltage, depending on how you want to phrase it. And you may have to do your spark gaps the same way, because if their voltage tolerance is only 6,000 volts, but let's say in operation it's running at 30,000 volts, you may have to do 5 spark gaps all in line, in series with each other, in order to get them to fire at the same time and to get their voltage level on each spark gap down to within their tolerance. These are all things you got to consider. It's mind-blowing, the complexity of actually building the thing, and I heartily welcome you wanting to do so, but I've thought in advance of all these complexities, and I stay away from them. Now, it's enough for me just to get it to simulate and work, and then write the books and try to do the videos and try to inspire people, because it's a workload enough, and I've already covered that in another video. So that's my excuse for not building it, along with not having the money and not the expertise or the money to buy all the test equipment and whatnot. But it is a lot of complexity, and I've tried to think it all through to be able to warn you in advance so that you know what to expect. But you do have to think all this through, a lot of planning. It's not a good idea to tinker on the bench and just throw things together and let's just see what happens. I would not recommend it. Tesla never did it that way. Why should we? He simulated it in his brain, but he had a highly disciplined brain by the time he reached young adulthood, in which his fantasies that were so realistic he could reach out and touch them and believe that he was touching them. We would call that some kind of a psychotic illness in today's age, but to him, he put it to good use. But if you read his autobiography, that's what he had to do. He had to discipline himself so that he wouldn't leap off the roof of his childhood parents' homes carrying only an umbrella, thinking he could fly, and then have a very unwelcome greeting with the earth on his way down to teach him a strong lesson, that he had to discipline his mind. But he disciplined it so well so that his realistic fantasies, which are basically a very hefty simulator for a brain, he could simulate something and then tell an assistant. He wouldn't do it. He'd tell an assistant how to build a thing, and it would work first time every time. Never failed. We don't get that. We get microcap that costs $5,000, and we pray that it's going to be as close as possible to reality so that I did most of the work, hopefully, and you don't have to tinker around and make a lot of foolish errors. Let's hope. All we can do is hope and pray, because I can't guarantee you anything. Not a dime, not even not even a wooden nickel. I can't even guarantee you that. Okay, let's see what else. Gee, I've covered a lot. So you may have to go out and get an analog sine wave generator. A digital may not work. Now, digital sine wave generators are meant to approximate a sine wave, and they may do a pretty good job for most people's experiments. But for this, we don't know if it'll work, because the simulator creates a perfect sine wave. And the only time you get a perfect one is with an analog generator. And I haven't looked around on the internet to see if they even exist. You know, Eric Dollard has said a lot of equipment has disappeared from the good old days, you know, vacuum tubes and whatnot, that he glommed from various military installations, warehouses that he had access to, or Bell Labs or whatever it was that he said or RCA Labs that he said he had access to. A lot of that stuff has disappeared, he said, and is impossible to get a hold of. But you may have to get something exotic if you can, or build it, or if you can't build it, try to fetch it. Because, you know, this is all stuff, this is one of the reasons why we don't have over unity, is sometimes you've got to, you know, John Bedini, well, Eric Dollard tells us that he grew up and one of his aunts worked in a vacuum tube factory, and so he worked there, and he got first-hand knowledge of how to build vacuum tubes. And then John Bedini was into material sciences. He was into the earth, geology, and he did various investigations in that area, because sometimes you have to build your own stuff. There's no way around it. So there are people on the internet who tell you how to build your own capacitors. I managed to do it for bionic circuits, but for building it for a power circuit is a whole other deal. You know, it's something you may have to look into. I covered it in my chapter, but I didn't really cover it very well. You may have to do some thorough searching, because I have found some sites on the internet that tell you how to do it. You know, you have to immerse the whole arrangement in a barrel of oil. You got to compress it in a vise, and you got to shake it and get the air bubbles out. I mean, it's a whole big deal, because you don't want air bubbles between your plates and your polyethylene dielectric film, you know, that you're sandwiching between your plates. So it's a whole big deal. So I don't know what you're going to have to do to get things to work. But you have to look at all these options. And again, it's all a question of exhausting all of your options. And that's worth repeating, even to the point of boredom and tedium. Because in the last analysis, I can't give you all the answers. You're going to have to find them yourself. Okay. That's not a nice note to end on, but let's see what else, if I've covered everything. So, if you've seen my pitch deck, I'm not sure if you've seen it or not. I cover voltage. No, it's in the chapter on solution. It's called, well, now I've called it proof of concept solution, because it's not really a solution. It's a proof of concept, because it creates a surge that might power a lamp, but certainly will not power an inductive load. And it was scaled down to operate at a table model size. And I had to throw away voltage to do it. I had to use a voltage divider at the sine wave generator area of the circuit to make sure I fed the surge area of the circuit, the solenoid coils, only microvolts of a sine wave. Because anything higher than a few microvolts killed the surge. Didn't allow it to happen. It prevented it from happening. But that's because the whole circuit output, I had scaled it down so that the voltage coils were millihenries. I think they were like 300 millihenries total, divided among the 5 voltage coils or 6 voltage coils. And I believe somebody on the internet took apart and measured and calculated. His calculation of the voltage of the inductance of a ice cream machine motor is 150 millihenries. So I wasn't far off. I was just twice too much. But I was in the ballpark. So for the point of simulation, and that's the way I figure. If I'm in the ballpark, I figure I'm pretty good when I'm simulating. But that's the best I can guarantee you, that I'm in the ballpark. That's why I say you may have a little work on your hands, because all I did was do ballpark figures. And anyway. So when you scale the circuit down, there is that problem that you have to reduce your voltage input severely by throwing away your voltage input, using a voltage divider and 2 grounds. And that's why I found I had to put a capacitor on the back end of that sine wave generator and to block the flow of DC current, and then leave the other ground open to DC path. And that was the one with the 1000 ohm resistor to throw away most of the voltage, while the sine wave generator had a 1 ohm resistor. So that's how I managed to solve that problem. I think I had to do a few other... Yeah, I had to add the capacitor in parallel with the spark gap. That was the other. So whenever your circuit becomes too unstable, that's when you have to add things like extra capacitors in parallel with various other components. So when I added the capacitor in parallel with the spark gap, that was the reason why. It was, the definition from the conventional standpoint, their definition of overunity, they call it instability. And it's true. It blows up. That's instability. Or it goes comatose. That's instability. Yet that's what we want. We want that instability, but we want to regulate it. We want the liability, the responsibility to regulate instability. It appears to be foolish from the standpoint of conventional wisdom that we want to take on this extra responsibility, but the gain is overunity. The gain is free energy. That's the cost of free energy, is the added responsibility of managing an inherently unstable condition by design, by intent. That's what we have to look forward to. That's the cost, is the added responsibility. Now, in my scaled-down version of the table model, I computed that it may not even be necessary to run the sine wave generator off of a 12-volt battery. Because when you look at the voltage characteristics of a solar panel, and you look at how much voltage they put out on a sunny day, if you put it out in full sun, versus a cloudy day, which is comparable to having it indoors, comparable, not the same, you're looking at 2 to 1. Roughly. It's probably a different factor than that in terms of extreme. How dark is it if you take the solar panel indoors? And working it off of ambient lighting indoors. Whatever the lighting happens to be that you can function on, that you want to expect your circuit to function on if you take the circuit indoors. And you're running it off a solar panel as opposed to a battery. Because it can be done. It is technically possible. You just have to double or triple your solar panel. What would normally be used to recharge a 12-volt battery, instead you use 2 or 3 times as much, but only 12 volts and only a trickle, because it only takes, remember, we're only draining the sine wave generator a question of picoamps I've seen, or nanoamps at the most, because we're only going to be expending something like less than 100 nanowatts in theory, according to my simulation. And since it's 3 volts, that means the amperage is going to be something comparable to the watts, only slightly less. It's either going to be the low end of nano amps, or it's going to be in the pico range, probably not less than pico. So my best bet, it would be the highest probability is in the pico range. maybe in the low nano range. But if I wanted to play a safe guess estimate, somewhere, I don't know, somewhere around in there. So when we're thinking solar panels, we think about voltage, but you also have to think, well, how much does it take to recharge a battery, and how much amperage is going to be coming out of a solar panel if we want to replace a battery with strictly a solar panel to run this circuit under low light conditions, such as indoors or in a cloudy condition. Well, it doesn't take much. So the prospect of running the circuit off a solar panel in order to create the over unity power gain that we want to create to run either a minor appliance such as a blender or a toaster, or a major appliance such as an electric car, is not too much. And the prospect is hopeful. I want to use the word hopeful, that it may be possible to run this circuit off of a reasonable surface area of solar panels alone, and no battery in between. It's possible. It's possible. Now that's the best case scenario. The worst case scenario in an electric car situation would be to have this circuit in line with the battery pack, the pre-existing battery pack, and only use the circuit for cruising to avoid the use of the battery pack. Because that's how the bases, the Prius, the hybrids are based on. It was based on an experimental model that was done on my car back in its day, immediately prior to the development of the Prius by Toyota. And, well, not the development. They didn't develop it. Alan Coccioni developed it, if I remember his name correctly. It was Toyota who manufactured it. But he tested the RAV4 EV of 2002 and 2003 with a motorcycle engine, a little generator that motorcycle engine was rotating, and a small, I don't know, couple liter gas tank. And he ran the cable from that generator across, in other words, in parallel to the battery pack of the RAV4 EV, through that parallel connection with the battery pack to the motor, the twin AC motor, well, the motor controller, I should say, that supplied the power for the twin AC motor of the RAV4 EV of 2002-2003. And they found that at cruising speed on the freeway on level ground, 60 miles per hour, they needed to supply only 50 amps. Now the twin AC motor needed 345 volts, but it only needed 50 amps. So they rated their output of their generator at 60 amps for safety's sake, give them a little hedge room. And they found that not only were they able to cruise, but they were able to recharge the battery pack at the same time. And that's the whole basis for the Prius, for the hybrid, is that arrangement, is that knowledge. The only time he had to use the battery pack was accelerating, like going up a hill or accelerating into traffic, getting your car up to speed. Regenerative braking, forget it. You don't make much. You can do it, but you get like 5%. They say, oh, you get 15%. Yeah, right. In your dreams, 5% is usually what you get. That's been my experience. Anyway, be that as it may. So the worst case scenario is you may only be able to use the circuit in an EV condition or situation in which you use it only for cruising and not for accelerating. That's the worst case situation. But that would still be pretty good. That would be my hope for the worst case situation. I don't know. This is all in my brain, all in my head. I don't know. So I'm giving you a lot of stuff that you may not need to know. Well, not a lot of stuff, actually, just a few things you may not need to know. Most of it, I think, is pertinent. Let's see what else. I think that's as much as I can think of at the moment. If I have to, I'll make another video. Anyway, I made this video because you expressed an interest, and other people may have an interest. How do we go about building it? And so these are the kinds of things you have to worry about. Exhausting yourself, exhausting all possibility. Edison, 10,000 different trials until finally the 10,001st one, he decided to use carbonized, bamboo as his filament for his light bulb. Eventually he shifted to tungsten, but I mean, initially he had to come up with bamboo, carbonized bamboo as the filament of choice for his light bulb, and it worked. But that was after he exhausted 10,000 other possibilities, and he was ready to give up. But that's when it came to him, when he decided to give up. And so don't think giving up is the final answer. It may be the right attitude for your higher self, your guardian angel, to come in and say, oh, now you're going to listen to me, huh? Because you finally let go. You finally let go. Now I can talk to you because you will be listening. You will be receptive to your soul telling you what I want to tell you through your soul. Your higher self is you. It's your God you, trying to get through to you through your soul. And half the time we don't listen until we die and we're judged. Then we listen because all our senses shut down and our mind is oblivious to the world. Our mind is still awake, even though our brain is dead. But our mind is still awake, and while it still is associated with the body, then we're judged because we're listening. We don't listen when we're alive. We're too busy being distracted by emotions, mostly. Emotions involve us. As one of River Phoenix's lines in the 1985 Explorers movie with Ethan Hawke, River says, you can't be emotional when you're being a scientist. Well, it's true. You have to be dispassionate. Now, sometimes that makes scientists cruel. Nazi scientists, they were being dispassionate, but they were being cruel, too, at the same time. We don't want to do that. But we do have to calm down the mind, one way or another. Because you can't get excited, as River says, when you're doing scientific experiments. You can be excited, for about 5 seconds or an instant when you perform an experiment and it does wonders for you, But when you're trying to test something and figure out what you're doing wrong, you can't afford to be excited. And you can't afford to be disheveled and depressed either. And that's why letting go and giving up is a useful stance. It doesn't mean it's the final answer and you have to totally give up. It just means you have to let go and be in a receptive condition to listen to your soul trying to help you, your guardian angel help you through your soul to give you the answers you need to solve the problems. Because I may not be there to help you, and I may not be capable of helping you. And your guardian angel is totally equipped to help you. Trust me, it is. It's divine. It's totally equipped. So most of our problem is our lack of receptivity. And they knew this in the days of Lemuria, and they knew this in the days of Atlantis. This is how they functioned. They didn't have an intellect. We have an intellect. That developed with the early Greek civilization, the intellect. The Atlantean and the Lemurians, they didn't have an intellect. They couldn't reason their way through a problem. All they could do was intuit or know from experience. Otherwise, they were clueless. And so they had long lifespans to make up the difference. We have short lifespans, but then we have an intellect to make up the difference for our short lifespan to help speed things along. So it works to reason. It always works to reason our way through something. But when we've reasoned through all options and can't think of a solution, then we have to rely on intuition, and that's when we have to fall back on our older ways of doing things. And that means letting go. And if it means being totally convinced, and you have to do this as an exercise. You have to think of yourself as a method actor. Think of yourself as Meryl Streep, in which you what's the guy's name? Oh shit. Nick Nolte. You have to get yourself totally in character, and that means you have to totally believe in giving up. If you want to if you have a problem with receptivity in achieving some intuitive hunch to get an answer to your problem, you literally have to convince yourself okay, that's it. I'm a failure. I can't do this. And be on the point of tears, Because it might take that in order to become receptive totally receptive to your soul, to allow your soul to convey to you what your higher self is trying to instruct you on how to solve the problem. Okay, I think I've covered everything, technical and attitudinal, psychological. Yeah, I think I've covered enough. So you can start with that and see if it's enough. You got any questions, ask. I'm here for you. Ask questions. I don't know. What can I do? I can't offer much better than that. All right. Thank you very much for listening. And now I'll shut up.